What about sampling with replacement? A cereal company put one of 5 different cards into each box of cereal. Each card featured a different NASCAR driver: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, Jimmy Johnson. This is already outdated because Jeff Gordon has retired. Suppose that the company printed 20,000 of each card so that there were 100,000 total boxes of cereal with a card inside. If a person bought 6 boxes at random, what is the probability of getting 2 Danica Patrick cards? Okay, so what binomial setting condition is violated in this situation? So let's think about what the binomial situation is. So B, we have what's the probability of getting 2 Danica Patrick cards? So we have the success is getting Danica, and the failure is not getting Danica. Okay, we have a fixed number of trials if a person brought, or independence, and independence is actually what's violated here. We do have a fixed number of trials, n equals 6. We have the probability of success of getting a Danica card would be 1 out of 5 because we have 20,000 out of 100,000. So prior to the prior probability, the initial probability is that any card that you drew would have a 1 out of 5 chance, but independence is violated here. The independence, okay, when we choose one box, the probability changes for the next. So we start out with 20,000 Danica cards out of 100,000, but then we draw a card. Let's say the card we draw is a Danica card, or even if it's not, if it is a Danica card, then we'd end up with 19,999 over 99999. Okay, so it changes. It changes from this to this. Okay, so each time you draw one, it just changes the probability a little bit. So it's not independent. So why is this a problem for statisticians? Because we often sample without replacement from a population. Just think about any time you sample people from a population, you aren't resampling, you aren't putting the person back in and choosing again and being able to get the same person twice. You're sampling without replacement. So this is done all the time in statistics. So how do you deal with the fact that that violates the independence condition? Technically, why is this really not a problem? And you might look at this and think, well, it's really not a problem because the difference in probability between 20,000 over 100,000 and 19,999 over 99,999 is so very slight that it really doesn't make much of a difference. And that is exactly the issue. That is exactly the same. The change in probability when n is very large, when the population is very large and the sample size is small, is negligible. In other words, it doesn't make much difference. Negligible. Okay. So if you actually calculated the probability, it turns out this is how you do it. First of all, we look at the probability of selecting 2 Danica cards out of 20,000 and then 4 cards out of the other remaining 80,000. So this is actually 20,000 C2. This is like the NCR thing on your calculator. 20,000 select 2 and then 80,000 select 4. So the probability, so this would be all the different ways we could select 2 out of 20,000 times all the different ways we could select 4 out of 80,000, all divided by the total number of ways we could select 6 out of 100,000. This is actually how you calculate the exact probability, and that would be right here. Now, if we use the binomial model to calculate the probability, we would say n equals 6, probability of success is 0.2, 1 out of 5, and we want to find the probability that x equals 2, 2 out of 6. So we would have 6 select 2 times 0.2 to the second times 0.8 to the fourth. And if we do this on our calculator with binom PDF, 6.22, we end up with 0.24576. Okay, how close are those? Very, very, very close. There's essentially no difference. Now, this happens to be a very, very small sample out of a very, very large population, so that makes sense. So at what point is the population large enough and the sample size small enough so that we can say, hey, it really doesn't make much difference? And here's the rule of thumb. If the sample size n is less than 10% of the population size capital N, then we can consider the trials to be independent. And I'm saying that consider is the word. We can consider the trials to be independent even though we are sampling without replacement. So when we're sampling without replacement, the trials are not truly independent, but we can consider them to be, because the difference in probabilities is slight enough that it's not a problem. So basically what you would test in here is we need for is 6 less than 0.1 times 100,000? Yes. Okay. So that satisfies the condition. So earlier we looked at choosing 5 cards from a deck of 52, and 5 is technically less than 0.1 of 52. So this actually barely satisfies the condition. So we'd have to look and see if those two probabilities were the same. And I'm out of curiosity, I think I will. Okay, so we said x equals the number of red cards out of 5, and so the probability of P would be 0.25, no, 0.5, I'm sorry, because half the cards are red, so 0.5, and n equals 5. And let's investigate the probability that x equals 4, that we get 4 red cards. Okay, so we would have, you know what, this one's going to get kind of complicated if we do it the exact way versus the other way, so I may have to stop here and think about this one. I had to kind of think through how to do this. So here would be using the binomial model. So if x is the number of red cards out of 5, probability is 0.5, n is 5, and the probability that x equals 4 would be 5 selects 4, 0.5 to the fourth, and then 0.5 to the first, because the probability of success and failure would be the same. Here would be how I would do it, just using strict probability rules. It would be 26 out of 52 for my first selection. Let's say I draw a red card. Then it would be 25 out of 51 for the next red card, then 24 out of 50 for the next red card. So now there's 23 red left out of 49 possible cards. That would be my 4 red. And then for the 5th card I drew a black card. Well, there's still 26 black cards left because I haven't drawn any black cards yet, so 26 out of 48. But just like the ones we've done in the past, I wouldn't necessarily draw red, 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 black. I might draw red, black, red, 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 or something. So these 5 numbers would still be in the numerator, and these 5 numbers would still be in the denominator, but the order could be switched around 4 different ways. Actually, it'd be 5 different ways, and I think I calculated it. That would be times 5, because there's 5 different ways to get 4 out of 5. So I need to go back and actually change what I did here. This actually makes more sense. Oh, I did it times 5. Okay, I just wrote it here. So here's what I typed up, and then I multiplied it times 5, and then I did the binomial model. Notice these aren't quite as close as the other one, but they're still pretty close. This is about 15% versus about 15.6%. So once again, if you were using the binomial to estimate, it would still be a pretty decent estimate. That's about as close. That is using the 10% condition for probably the farthest away case, but it still does work. It's still reasonably close. So I wanted to show that, and I'm going to copy that. I already have it copied and pasted into my notes because I think that would be helpful to see. I hadn't actually calculated that before, and it's nice to know that that is still reasonably close. So the 10% condition, you just have to check that your sample size n is less than 10% of your population size. And if that is the case, then you can violate the independence condition because the probabilities are close enough even if the independence is violated.